Hello friends, a very good morning, good afternoon and good evening to all of you. I am Preeti Sumandas inviting you to another very important and useful topic from your syllabus. Friends, I hope you do remember in our last class we had covered types of units. What are the base units, what are the derived units and different types of derived units we had discussed. And I request you all, if you have any doubt, please ask me in the comment section so that I can clarify your doubt and I'll help you in that manner. So in this video, we will be discussing about another very important topic from your first chapter, that is significant figures. This topic is very important because questions come from this topic. You have to be very mindful to learn this topic. Sometimes students get confused about these significant figures because there are several rules how to determine significant figures. I will tell them very easily so that you can remember them, but before that you have to convince yourself why you should study significant figures. What is the need of studying significant figures? For that, I will tell you from the beginning of the story, that is from my first video, I told you that physical quantities are those quantities which can be measured. So in physics, we are doing experiments. In every experiment, we get observation values. So in those observations, what are we using? We are using different apparatus for doing different experiments. And those observation values are always not equal. We are getting different observation values for different time of observation. Why so? Because the exact value of an experiment cannot be obtained every time because our measurements contain errors. Errors may be due to our measuring apparatus, may be due to our personal negligence, or may be due to some random things like for example, while you are doing any experiment related to electricity, then if the power supply goes off and again it comes up, then there will be a fluctuation in your reading. So there are several errors in our measurements while we are doing any experiment. That's why our lab experts tell us that take several readings and then find out the mean value, so that you can see how accurate your value is and how precise your value is. Two things are there, accuracy and precision. So, accuracy and precision, these are two different things. What accuracy is and what precision is, we will learn from this example. Suppose I have this marker and I have to measure its length, and I am given with a scale. This scale you know, which is in your geometry box. So I have to measure the length of this marker with this scale. Now I am measuring the length of the marker. So I am coinciding this end of marker with the zero of the scale and taking the reading of the marker, and the other end of the marker is meeting the scale at 13 centimeter, and it is meeting like this. I will show you. So if this is my scale and this is the zero of my scale, then the marker's length is coming up to the street. It is coming up to here is 13 centimeter. 1, 2, 3, 4, 5, 6, 7, Okay. So my marker pen's length is falling from, I am coinciding the end of the marker to the zero of the scale, then my marker pen's length is coming up to this point. Okay. Can you see up to which point my marker pen's length is coming? It is at 13 centimeter. 1, 2, 3, 4, 5, 6. It is in between 6th division and 7th division. So in this case, what I will learn that, I will tell that length of my marker is in between 13.6 to 13.7, or I will think that it is, in my opinion, it should be towards 13.6. So I will mention it as 13.6 centimeter. One of my friend, Chandni, came and she took the same measurement. She told me that length of the marker is not 13.6, it is towards 13.7 centimeter. Okay. Then my teacher came and my teacher told me that you both are wrong. The length of the marker is actually actual length of marker I will mention. Actual length of marker is equal to 13.68, sorry, 13.603 centimeter. Okay. So in this case the measurement is not perfect. In this case it is also not perfect, and this is the true value. Another friend of mine, Shushmita, came with a different scale. Her scale has, in my scale, what is the least count of my scale? What do you mean by least count? Least count is nothing but the minimum measurement you can take with your scale. Suppose in my scale, as you know in your geometric scale, what is that? This 1 centimeter is divided in how many parts? 10 divisions. So 1 centimeter is equal to 10 divisions. So I can write 1 division correspond to 1 centimeter by 10 or 0.1 centimeter. So this is the least count of my scale. Okay. So this 0.1 centimeter is the least count of my scale. Susmita came with another scale which has 100 division in between 1 centimeter. In between every 1 centimeter, in her scale there are 100 division. So her scale's least count will be what? Her scale's second scale. Okay. In her scale, 1 centimeter is equal to 100 divisions. Okay. So 1 division in her scale will be equal to 1 centimeter by 100 or 0.01 centimeter. So while she measured this marker pen's length with her scale, she found that the length of the marker pen is coming like 13 point, this is observation 1, this is observation 2 and another observation 3, which is done by my friend Susmita, and who has a different scale with different least count. She found that length of the marker is equal to 13 point. In her scale, what happened? 6, 2, she found in her scale. The measurement is after 13 centimeter it goes up to 62 number division. So she wrote that in her scale the length of the marker is 13.62. Okay. So these are the observation we got from different observer and using different scales. In these cases what happens? In case 1 and 2, although the observations are close to the true value, but their precision means the value up to the minimum value that has been read. So here you can read up to first decimal number. You can't read up to 3 decimal number. So here precision is less because the scale you are using, it has lesser precision. And in this case precision is higher than these two values because the scale used in this case, it has higher precision in comparison to this scale's precision. So precision is directly connected with the least count of an apparatus. So these two values, although they are close to the true value, they are not much precise, but this value is more precise because it can read up to second decimal number. Okay. So precision and accuracy are two different things. First, accuracy gives you the measure of how much amount your measurement is close to the true value, actual length in this case, a true length of the marker. Whereas precision gives you up to what resolution, up to what limit your apparatus has read the measurement, or up to what resolution, or what it is related to the least count, as I said, up to what limit your apparatus is able to read that quantity, measure that quantity. So these two things you should keep in your mind, that accuracy and precision are different things. After knowing accuracy and precision, we will think why I am saying madam is telling us about accuracy and precision. Actually, as we have discussed, in physics, every measurement is not obvious. Every measurement contains some error. So we have to take the measurements in such a way that they should be more precise. So while measuring, our measuring instruments should be more precise so that we can get a precise result. But what happens sometimes? Sometimes while taking measurements, what happens? Due to this precision, we get results like 1.2346058, long values. We use calculators and we can get this type of value. Suppose this is this much meter of a length, the length is found to be this much. Okay, so in this case, by writing this long quantity, this long quantity of measurement, it is quite confusing and misleading for the observer how to take such length. So we have to find out how many numbers in this measurement are significant. So to know the perfect measurement, up to which extent we can consider the measurement is perfect, the significance of the measurement can be done by knowing the number of significant figures in that measurement. For that, we have to follow some rules which are governing the number of significant figures. So, for that, we have to keep in mind that first thing is, in a measurement, what happens? We have two types of digits. Some are reliable digits and some are doubtful digits. What are the reliable digits? Suppose in a measurement you have the reading of 12.58 meter. So in this reading up to 12.5, you know that the measurement is okay. But this 8 centimeter, it is doubtful. For example, just I took my marker's length. So in the first measurement, what I found, in first measurement I got that the length of the marker is 13.6 meter, and my friend found that it is 13.7 meter by using this scale. So, and third friend found that it is 13.62 meter. So, up to this 13.6 meter, it is absolute. Okay. And this 2 meter may be right, may be wrong. It is doubtful because my scale's precision is not that much efficient to read this 0.02 centimeter. So, what are the significant digits here? The reliable digits. This is also the reliable digit, 13.6. These are the reliable digits, and the first doubtful digit. First doubtful digit is the next digit which is next to our last reliable digit. In 13.62, 1, 3, 6, these three are reliable digit, and 2 is the doubtful digit. So the rule number 1 says that you have to consider all the reliable digits plus the first doubtful digit. So in this number 13.62, there are how many significant digits? Significant digits. So reliable digit 1, 2, 3 plus 1 doubtful digit is 2. So total is there are 4 significant digits. By saying this, it is not easy to understand because so many numbers, so many measurements we come across with. So to know properly which number are significant and which are not significant, we have to read them, we have to study them carefully, and then by following the rules, we can understand how many significant digits are there in that measurement. For that, we have to write down the rules. First, you will see one by one rule, and we will take examples by which you can understand the concept very smoothly and easily. So, first, the rule says that a change in units will not change the number of significant numbers or significant figures in a measurement. A change in unit will not change the number of significant figures in a measurement. Suppose you got a measurement that the length of a rod is 12.63 meter. Okay. So how many significant numbers are there? 1, 2, 3. These are reliable digits, and this is the first doubtful digit. So you will tell that total number of significant digits, significant figures is number of significant figure is 1, 2, 3. This is reliable. Number of reliable digits plus first doubtful digit. So the total number of significant figures here will be 1, 2, 3. 3 plus first doubtful digit, that is 4. So the rule says if we change the unit, then the number of significant figures will not change. What do you mean by change the unit? Here the unit is in meter. Suppose I will write it in centimeter. So you know 1 meter is 100 centimeter. So 12.63 meter will be 1263 centimeter. Now what is the length? What is the number of significant digits here? Here the significant digits will be also 4. Suppose I will convert it into kilometers. So 1 meter is how much kilometer? 1 by 1000 kilometer. Okay. In 1 kilometer there are 1000 meters. So I'll tell that 1 meter is equal to 0.001 kilometer. So 12.63 meter will be equal to 0.1 into 0.001 into 12.63 means divided by, okay, so it will be 0.01263 kilometers. So this is 0.01263 kilometers. So in this case also the number of significant digit will be 4. How? We will understand this by applying some other rules. Here you see that there is a 0 here, then 1, 2, 6, 3. So you can think that this is also a significant number, isn't it? But why the rule says that there are only 4 numbers? Here 4 numbers, here 4 numbers, here also 4 numbers. We will understand these by studying those rules. So first rule says all the non-zero digits are significant. For example, first rule says all the non-zero digits are significant. Okay. For example, if there is a measurement like 1, 2, 3 kilometer per hour, then here how many significant digits are there? 1, 2, 3. 3 significant digits. Because all the digits are non-zero. Among these 3 digits, no digit is equivalent to 0. Similarly, we can say 506, sorry, not 0. 5, 7, 6, 8, 9, 7. Hour. How many significant digits are there? 1, 2, 3, 4, 5, 6. We will mention 6 significant digits are there. Okay. Here 3 significant digits. When the measurement value doesn't contain any 0, then the measurement reading will have the number of significant digits which is equal to the total number of digits in that measurement. If we are having 7, 3, 2, 5, then this is 4 significant digit in this measurement. If we put a decimal here also, the same 4 number of significant digits we will get. If I am mentioning it as 7.325 also, I will get same 4 number of significant digits. In this case, or in the 0.7325 case, also you will get, okay, we will discuss it later because 0, we are considering only non-zero quantities. So if I write 732.5, also here also we will get 4 significant digits. So it is very simple. All the non-zero digits are significant. Okay. Next, we will go to the next rule, which is little bit complicated, but not that much. You can get it easily. Second rule says, all the zeros between two non-zero digits. Second rule says, all the zeros between two non-zero digits are considered as significant. Okay. So what you understood? All the non-zero quantities in between all the zeros between two non-zero digits are considered as significant. Yes. No matter where the decimal point is. So what is this? All the zeros between two non-zero digits. Suppose here 1, 2, 0, 0, 3.56. It is a quantity measurement result, and you have to find out the number of significant digits. So as per the rule, here these two zeros are situated in between two non-zero quantities. What are the non-zero quantities? 2 and 3. So if these zeros are in between two non-zero quantities, then these zeros will also be considered as significant. Again, what it tells? No matter where the decimal point is, the position of the decimal point will not affect the number of significant digits if the zeros are in between two non-zero numbers. So, from this example, can you tell me how many number of significant digits are there here in this question? Number of significant digits here will be 1, 2, 3, 4, 5, 6, 7. Okay. Why I considered this also? Because up to this point, these are real, these are I can say reliable digits, and it is the first doubtful digit. So all the reliable digits plus one doubtful digit. So I can say it is 7 number. 1, 2, 3, 4, 5, 6, 7. Same quantity. If I write it like this, 12.00356. Again, these two zeros are in between 2 and 3, which are non-zero. So in this case also, number of significant digits will be 7. If I put 1.200356, even here I can say that number of significant digits is 7. So got my point? All the zeros in between two non-zero digits are considered as significant. Next rule. Third rule says that if the number is less than 1, if the number is less than 1 means it is a decimal number, right? Okay, if the number is less than 1, then all the zeros on the right of the decimal point, but to the left of the first non-zero digit are not significant. But the trailing zeros will be significant. Okay? Trailing zeros means what? Those zeros which are in the last of the number. We will take an example. What does this rule says? Here first line says that if the number is less than 1, suppose the number is 0.053200. Okay? As per the rule says, this 0 is after the decimal and it is right to the decimal, and it is on the left of the first non-zero digit, which is 5. This is the first non-zero digit, first non-zero digit, isn't it? And this 0 is on the right of the decimal point and before the first non-zero digit. So this 0 will not be significant. This is not significant. Okay? But the trailing zeros will be significant. So if there is a decimal point and the end of the result is having zeros, then these zeros will be significant, will be considered as significant figures. Got it? So in this case, how many significant numbers you will get? Tell me. This is non-significant. This is significant. This is significant. This is significant. And also these two trailing zero. Trailing zeros means those zeros which are at the end of the number. Trailing means at the end. So these 1, 2, 3, 4, 5. 5 number of significant digits are there. In this case, there are 5 significant digits. Okay? We can take another example also. Suppose another number is there which is 0.000785. Can you tell me how many number of significant digits are there? Yes. These zeros are on the right of the decimal point and before the non-zero digit. So these 3 zeros will be considered as non-significant. So how many number of significant digits will be there? Only these 3 digits are considered as significant. So there are only 3 significant figures. Yes, we will take another example. Another example. Suppose 0.050206. This is the number. You have to find out how many significant figures are there. So tell me which 0 will be significant and which will be non-significant. Yes, very good. So this 0, since it is on the right side of the decimal point, this will be considered as non-significant. And it is on the left side of the first non-zero digit. But this 0 is following the first rule that we had, second rule that we learned now, that in between two non-zero digits, if a 0 comes, then it will be considered as significant. So this 0 will be significant. Also this 0 is in between two non-zero digits. So this will be also significant, and this 0 is the trailing 0. So it will be also significant. So in this case, how many significant digits are there? 1, 2, 3, 4, 5, 6. Here 6 significant figures are there. Clear? Okay. I hope you got the concept of this rule. We'll go to the next rule. Okay. Next rule says, if the number doesn't has any decimal point, if it is a pure number which doesn't have any decimal point and it has trailing zeros, then those zeros will not be considered as significant. Rule number 4 is, if we have a number without decimal point, we have a number without decimal point, then the trailing zeros will not be considered as significant. This is just the opposite of the previous rule. In previous rule, we show that if there are trailing zeros after decimal point, then those are considered as significant. But this rule says that if you have a non-zero number, if you have a number without any decimal points, suppose you have 1200. So this number doesn't have any decimal point and it has two trailing zeros. Then in this case, these two zeros will be considered as non-significant. What they will be considered? Non-significant. In case of decimal, the trailing zeros were considered as significant. But in case of number without decimal point, the trailing zeros are mentioned as non-significant. So in this case, the number of significant digits will be only 2, 1 and 2. For another case, I can write 2350000. In this number also, you will say there are only 2 significant digits. And these 4 zeros are non-significant because they are at the end of the number and called as trailing zeros. Well, after reading these rules, sometimes another confusion arises. What is that? Suppose you have a number with trailing zeros. These trailing zeros make confusion. How? Suppose you have a measurement of 47.00 meter. Okay. Then here you will say that since these 00, these are mentioned explicitly, so these are all 4 significant digits. Okay. And when you will convert it into centimeter, then you will multiply this with 100. 1 meter is 100 centimeter. That's why you will get 4700 centimeter. Here the number of significant digits will be also. Here the number of significant digits, you will think that the number of significant digits is 2. two significant digits, because as per the rule, the trailing zeros with in a number which doesn't have any decimal point are not significant. So in this case only 47, 4 and 7 are the two significant digits. But our first rule says if you are changing the unit, there should not be any change in the number of significant digits. This is quite confusing. How can this happen? For this reason, to eradicate this ambiguity in determining the significant numbers, what we do? We write every measurement in a scientific manner. In a scientific manner means we represent a measurement as in the form of A multiplied by 10 to B. Okay, A is a number representing numbers between 1 to 10, and this B also some power of 10. It is a number, maybe positive or maybe negative. Positive or negative. For example, in this case, if we write 47 meter as 4.7 into 10 to power, I will write 10 to power 1 meter. And now if I convert it into centimeter, then I will keep this part, 4 part same, but I will just increase it as 10 to power 3 centimeter, because I know 1 meter is 10 to power 2 centimeter. So while this much value and this much value both are same, it will give you 47 meter. Also this will give you how much? 4700 meter means 47, sorry, centimeter means 47 meter. So what we do? We represent every quantity in the form of A multiplied by 10 to the power B, where A is represented as a number in between 1 to 10 and B is the power. Apart from these laws, there is another important thing you should remember. The multiplying and dividing factors in a measurement are exact numbers, and they can have infinite significant figures. Which means, for example, you are given that the radius of a sphere is, you are given as 2.569 centimeter, and you have to find diameter. What you will do? You will multiply 2 with 2.569 centimeter, and the resultant you will get 13 to 10 to 5 point. So here what you will get? 1, 2, 3, 4. 4 significant number. But if you are told that how many significant figures are in this 2, then you can't say the number of significant figures in it, because this 2 is an exact number. You can write it as 2.0, otherwise you can write it as 2.00, also you can write it as 2.000000. Okay. So for exact values, the number of significant digits are infinite. So wherever there is a exact number, suppose radius is equal to diameter by 2. So this 2 have infinite number of significant figures, because this 2 is an exact value. You can represent it with infinite number of zeros. You can't say that it has only one significant figure or two significant figure. So for exact values, the number of significant digits is infinite. Okay. Now we will see, while we are operating some arithmetic operation with our digits, with our measurements, then we have to keep in mind two laws which are applicable for arithmetic operations like multiplication, subtraction, addition and division. Basically, one law is applicable for both multiplication and division, and another law is applicable for subtraction and addition. First, we will see the law for multiplication or division. Okay. So, when you are doing any multiplication or division, then your resultant value should have the number of significant digits which is equal to the least number of significant digit in the question. For example, suppose this is a box and inside this box 2.23 grams of substances are there. Substances mass is 2.23 grams and the volume of this box is found to be 3.1 centimeter cube. You have found that this is the mass of the substance and volume of the box is 3.1 centimeter cube. And you have to find out the density. Then you will divide this quantity with the volume of the box. So after dividing you will get a number like this. Here are more numbers also. Then how much, up to which point you have to, up to which digit you have to write? You will write up to that digit whose significant number of digits are matching to the least number of significant digit in the question. So here in between these two numbers, which number contains less significant digit? Here number of significant digit is 1, 2, 3, 3. Here how many significant digits are there? 1, 2. So our result should contain as much the number of significant digit which is less in the data. So this quantity should be expressed in terms of only two significant digits. So we can write the answer as 0.7. Since 1 is here and 9 is here, we will write it as 2. We are rounding off it to 2 and we will eliminate other things and we will write here 0.72 grams per centimeter cube. We will learn rounding up. In addition and subtraction, we have to see which data has the least number of significant digit after decimal. Okay, in multiplication and division, after decimal, before decimal, it was not considered. It was considered as a whole quantity should contain that quantity which has least number of significant digit either before decimal or after decimal, but we have to consider them all together and we have to find the number of significant digit. And here we are considering the significant digits after decimal only. Okay, so suppose we are adding two quantities, 1.253 plus 0.62. Then the addition will be like this, isn't it? Which number is having least number of significant digit after decimal? This number is having less number of significant digit. Here significant digits are 2, here 1, after decimal significant digits are 3. But our result is having 3 significant digits after decimal. So we have to write it as 1.87 because 3 is there. If the next number is not above 5, then we don't have to think, we have to write the digit as it is. We will discuss it in the next thing. So here the result will be 1.7. It was an easy example. Suppose another example I am giving you. Suppose you have to add 0.256 with 5.32. Okay, well, let it be 6.256. So when we will add it, we will get 6, 7, 5, 11. So what is the number of least significant digits after decimal? This number contains least number of significant digits after decimal. So how many number of significant digits are there here after decimal? It is 2 significant digits. So our resultant will have 2 significant digits after decimal. We will not think about the digits before before decimal point. We will think of the digits after decimal. So we will write 11.57. Okay. Similarly, if we are doing subtraction, suppose we are doing a subtraction 57.653 minus 41.32. Okay, so what will be the result? Okay, then 6, 1. So here also we have to consider the least number of significant digits. So here this is the least number of significant digits, that is 2. So we have to mention our result as 16.33. Okay, got it? If you need more examples, then please let me know. In another video, I will tell you some other problems also which are dealing with this arithmetic operation. Next, we will see rounding of the uncertain digits. Uncertain digits are nothing but the doubtful digits. Okay. While we are doing measurements, sometimes we get long figures with so many number of uncertain digits or doubtful digits. For example, we are getting, suppose in a measurement we are getting a result of 6.1352789925. So this is a very huge number. It is not easy to use this number for further calculations. So we need to round off the significant uncertain digits. In the question, you will get that round up the number up to 2 decimal points or up to 3 decimal points. So in such questions, suppose there is a question, round up this number up to 3 decimal points. 3 decimal points. So round up to 3 decimal points. Up to 3 decimal points means you have to round up this number up to 1, 2, 3. 3 decimal points. So there are some simple rules. I think you know those rules. You have used those rules in your school levels also. Again, for just revising, I will tell you. In this case, what you see, the number is 6.13. Up to this number, we can say this is significant. And after this, since it is asking up to 3 decimal points, so we will consider it as the doubtful point, doubtful digit. And after that, there are a long number of digits. Okay. So if these numbers are below the value of 5, here 2 is less than 5. 2 is less than 5. So if it is less than 5, you will write as it is. Okay. If the number is less than 5, then you need not to think much. You will just write it as it is. Suppose here I am erasing this 2. The number is like this, 1.35789925. And the question is saying round off up to 3 decimal points. Here after 5, which number is there? 7. So 7 is greater than 5, that is number is greater than 5. So in that case, what you will do? You will add 1 to this 5. So the rounding of result will be 6.136. Basic and simple rule. If the decimal point, last decimal point, which should be rounded off, which need to be rounded off, if after that decimal digit a number is there which is less than 5, then you will write the number as it is. But if the number is greater than 5, then you will add up 1 and you will write the number. Another example, suppose there is a number 5.00351. So in this case, you have to round up to 2 decimal points. Okay, up to 2 decimal points. So what will be the answer? 2 decimal points means you have to write up to this. And the next number is here 3. 3 is less than 5. So you have to write the answer as it is. You need not to add 1 here to this digit. So the answer will be 5.00. But if it were 5.00851, then in that case, while you are rounding up to 2 decimal point, you have to write 1 because 8 is greater than 5. Got it? So, considering this rule, you can round up the decimal points, decimal digits up to which the question is asking. And another very interesting and little bit confusing rule is there. We will see that this is the case of when the next digit is either less or either greater than 5. It is simple, pretty simple to get the rounding of digit. But when the digit is 5 only, suppose you have a number 5.632559. Okay, and you have to round up to 3 decimal points. Up to 3 decimal points. Then up to 3 decimal point means up to 2. Next number is what? 5. So 5 is neither less than nor greater than 5. It is equal to 5. In that case, what you will do? Yes. In that case, if the preceding number is an even number, then you will leave the number as it is 632. Okay? Got it? 2 is even, so you will write it as it is. In case of 2, if it were 4, then you will write 4. If it is 6, then you will write 6. If it is 8, then you will write 8. So, whatever the number may be, but if it is even and you are having a 5 after that and you have to find up to the 3rd decimal point, you have to round up to 3rd decimal point, then you will write the number as it is. Okay. Next case, if the number is not even, if it is odd, like 1, then what you will do? You will add 1 to it and write your answer 5.632. It may be 1, it may be 3, it may be 5. See, here 5, here 5. But you have to round up to 3 decimal point. So you are looking for this, you are checking this number. So this number, if it is 5 and here also you are having an odd number, so you have to add it up 1 with 1. So the result will be 6. And if it is 7, you will add 1 to it and you will get 8. And if it is 9, what will come? It will be 640. Isn't it? By adding 1 to 9, it will become 1 0. So that 1 will go to here. So the result will be 5.640. You have to mention this 0. Okay. So this is the rule. So these were the rule governing the doubtful digits, how to deal with the doubtful digits, how to determine number of significant figures in a measurement. So these all you have to read carefully. You have to practice some questions. If you insist, then I'll take another class for it for some problems. We can solve some problems also. Before ending this class, I will like to tell you one thing that I had left in my last class, that is for the class for units, types of units. I forgot to mention you that we have supplementary units also. So as I told you in my first class, supplementary units are used for, supplementary quantities. Supplementary quantities are used for geometric concepts, and we have two supplementary quantities which are plane angle and solid angle, and the units of plane angle is radian, and unit of solid angle is steradian, STARADIAN. I forgot in my last class to mention these two. You should remember this. So this was for today's video. My next video will cover dimension formula and dimension equations. Thanks for watching.